Okay, so it's a double bill, and the first speaker, of course, is my Atiyah. And he's done me the kindness of writing out the title of his talk here. It's elliptic operators, discrete groups, and von Neumann algebras. And that,
Actually, I think I wasn't quite the title of the talk when it came, but it will do. So let me explain this double bill. I wrote a paper in 1976, there it is, the title. And it's a long time ago, nearly 40 years ago. In the meantime, a lot has happened in the field which supplies. Big books have appeared on something. There's a very big book by
Wolfgang Lück.
book, yes, it's about 800 pages,
Yes.
and many papers and so on. And then this last summer, I was at an international conference and I met some young man from Germany, and he told me that a lot of results had been solved, or questions I'd raised had been improved, so I thought it'd be good to have up-to-date presentation of what's happened in 40 years. So it's quite nice to write a paper 40 years later. Well, you wait 40 years and some of the questions are answered. Poor old Fermat would have had to live for 300 years and couldn't make it. I lived long enough to see the answer. So I thought that it would make good sense if I gave an introduction, explain what the original paper was about, what the prominent questions were, then our visiting speaker obviously would bring it up to date on what's happened, progress, and so on. I thought it was very easy. All I need to do is to look at my whole paper, give a summary to you. But I discovered it's not so easy. You look at the paper you wrote 40 years ago, and you find it quite hard. And the guy who wrote that paper was much younger than I am. He could deal with technical questions that I forgot all about, and so it was really very hard. So I decided I couldn't quite do that. But what I'm going to do is to extract the essential ideas from it, and I will not leave out all the technical details, so I could hopefully don't make mistakes. Anybody asks them technical questions, I will ask Mr. Lucas over there to answer them when he comes to talk about it. It has the advantage that you don't need to worry with technicalities in my talk. Second thing to say is that the title of the elliptic operators, discrete groups, and von Neumann algebras, I don't want to assume that everybody in the audience understands all of those things mean. I expect most of you to understand what the middle one means, discrete groups. Otherwise, you may not know much about elliptic operators, and you might even know less about von Neumann algebras. So I will bear that in mind in my presentation. I will try to explain what's necessary. Secondly, to say is that much of the work focused later on is about not the general theory of elliptic operators, which is what my paper was about, but there's a very special case, which is special interest, which leads directly to topology, and that's the part which is mostly been studied. Now, when I came to start thinking about how to present this talk, I thought, well, I'll do it logically from the beginning. I'll explain what this is, what this is, what this is. But I realized that was hopeless because it was too much explanation, too much background. I'd never get anywhere, and anywhere I'd forgotten the details. So I thought I'd do the problem sideways. So I talked about some of the problems, historical problems, which have arisen and lead to these questions, and give you a kind of sideways entrance, not direct entrance. So sideways, I'm going to start with one of the most famous theorems in geometry and topology and different geometry, what's called the Gauss-Bonnet theorem, which really goes back to Gauss. I'm not sure who Bonnet was. Do you know who Bonnet was?
This was in 1840, was his
right, well,
but 20, 30 years after Gauss.
You find many theorems in mathematics are due to pairs. Gauss-Bonnet, Riemann-Roch, Peter Weil. And the characteristic thing is the first one of those was very famous. So Gauss, Riemann, Weil, they had thousands of theorems. How can you tell which theorem they were talked about when you tagged on the name of the other guy who was not well known, who didn't write any papers, and then you have a unique solution. So the Gauss-Bonnet theorem is really Gauss, but
well, it's clarified.
Well, all right.
There's one theorem taken away from it.
Well, quite often, like the chap was actually a student of the other man, and his thesis, and anyway.
Someone in the audience has mentioned Atiyah Singer theorem.
Oh, I would not me. There are some examples of people of equal age in the family. Now, so the Gauss-Bonnet theorem, what I'm going to talk about, let's take the simplest example, going back to Gauss, where you're studying surfaces. You have a surface, nice curved surface, think of it in space, compact. Well, you can take a surface with a boundary, which Caspar needs that also, but this is the case of a closed surface. So a Riemann surface with holes and handles, and it has a Riemannian metric on it. So if you think of it in space, it's just the metric induced from the space. Now the most important topological invariant, which is much older than Gauss, is of course the Euler characteristic. The Euler characteristic is defined on almost any topological space, it's a complex, doesn't need to be a surface. And the Euler characteristic, on the one hand, is defined as the alternating sum of the Betti numbers of the space, the Betti numbers of the ranks or dimensions of the homology groups. But it can also be defined more elementarily by taking a triangulation and counting up the numbers of vertices, triangles, and edges, taking the alternating sum of those. And this comes to be the same thing. And that's the form in which Euler would have dealt with it. The number of vertices of polyhedra and so on. Anyway, the Euler characteristic is a very famous topological invariant, and in the particular case of a surface, the homology only goes up to dimension 2, and the zero homology, the one dimension rank 1, and two-dimensional homology by duality rank also got rank 1. The only interesting one is in the middle dimension, 1, and there the answer is an even number, and it's twice what's called the genus of the surface, so the answer is twice 1 minus g. The genus of the surface is g is equal to 0 for a sphere, 1 for a torus, and 2 and so on for more things with more holes in them. So this is the Euler characteristic defined topologically, but the Gauss's theorem is concerned with the differential geometry. If you think of the surface with its metric, the Euler characteristic does not refer to the metric. If you take the metric, then the metric has, as Gauss discovered, a very famous invariant called the Gauss curvature, scalar curvature of the surface. This is a number defined on the surface from the geometry. It tells you how it curves, and you integrate total scalar curvature over the whole surface up to a factor of 2 pi, you get the Euler characteristic. So in this theorem, the left-hand side does not depend on the metric, the right-hand side depends on the metric. There's no topology, it's integration. So this is the famous theorem of Gauss-Bonnet. And it's the precursor of vast numbers of more complicated generalizations in higher dimensions of all kinds, of which the Atiyah theorem was one. One thing to note about this theorem, even if you know much about it, if you take this theorem, if the curvature of the surface is everywhere negative, then obviously the integrand is negative, so all the characteristic is negative. And if the Euler characteristic is negative, then you see the genus has to be at least 2. Okay? If you take genus 0, you get a sphere, the answer is plus 2. For a torus, it's 0. But for surfaces of higher genus, it's negative. And even if we didn't know what surfaces look like, it follows from the Gauss-Bonnet theorem that it has to be the case. And that's an important point to bear in mind when it comes to generalizing. Now the question is, all this talk is about, is what happens if you replace these compact surfaces X by a non-compact surface. Now non-compact surfaces, I tell people, non-compactness is not a property, it's the absence of a property. So to say something is non-compact tells you nothing. There are millions of ways in which it can be non-compact, and there's no universal theorem really that applies really interest, telling you all about all non-compact surfaces. You must decide which kind of non-compactness you're interested in. Now the kind of non-compactness I'm interested in here is simply the example of the universal covering of a compact manifold. And if the universal covering is so many copies of the original manifold with so many sheets, and if the number of sheets is equal to the order of the fundamental group, if the fundamental group is finite, it's a finite sheeted covering. But if the fundamental group is infinite, it's an infinite covering, and therefore is non-compact. And the kind of example I'm interested in is precisely like that, where this is the universal covering of a surface, but more generally something else. And in the case of Riemann surfaces, the universal covering, if the genus is at least 2, is well known to be just the unit wall, or plane topologically, but as a metric surface, if you take a metric on the constant curvature metric on the Riemann surface, what you get is the hyperbolic plane. That's a non-trivial theorem in itself. Anyway, these are the kind of surfaces I want to talk about, the last question is, what can you say about things like Gauss-Bonnet theorem for such universal covering? So the main result of this paper, you could say, is an extension of the Gauss-Bonnet theorem to universal coverings. Now, it uses the Gauss-Bonnet theorem talks about the Betti number. The Betti number is the dimension of the homology groups. If you take real coefficients, the dimension of the real vector spaces, which are finite for a compact surface. If you have a non-compact surface, then the homology, the corresponding things you want to calculate dimensions of, which we'll see in a moment, will typically not be finite dimensional. And so you have to have some notion of dimension which makes sense in that context. And that's what these von Neumann dimensions are. Now, von Neumann dimensions, I'll say a little bit about them, were introduced by von Neumann.
And Mari, they are called Mari von Neumann dimensions.
Okay. A good example of the second part. So the big theory, big beautiful classification of von Neumann algebras, but what the big surprise was that von Neumann started off trying to axiomatise Hilbert space projection operators and so on, and he expected to find just usual Hilbert space answers, but he discovered there was another alternative theory in which the dimensions came out to be real numbers, not just integers. And those are the kinds of von Neumann algebras that I'm interested in here. So, so there will be real numbers, and these von Neumann algebras occur in many contexts. But one particular context they occur is in the context of infinite discrete groups. That's the context we're going to talk about here. Also, the reference I had to elliptic equations and so on is going to be very specialized. We're only going to be concerned with sort of harmonic functions, with the theory coming from Hodge's theory about solutions of the Laplace operator or its extension to differential forms. Many more examples of great interest which I was interested in at the time. The theory applies, but we'll focus here only on the Hodge theory. So let me remind people here what Hodge theory is. Here we belong to something called the Hodge Institute. I think.
Yes, we do.
This is part of the Hodge Institute?
Yes.
Okay, good. So the Hodge theory says many things, but it says if you have a compact Riemannian manifold, then on that you look at the differential forms, exterior differential forms of the degree 0 up to the dimension. On those you have ordinarily defined exterior derivative, but with the metric you also have its adjoint. The exterior derivative is called little d, the adjoint is called delta, curly d, and if you form the composition d delta plus delta d, little d increases the degree of a form, delta is the adjoint, decreases the degree, so this combination preserves the degree. This is called the Hodge-Laplace operator. And it's a solution of the equations Laplace turn equal to 0 is called harmonic. And you have harmonic functions, harmonic 1 forms, harmonic 2 forms, up to the dimension of the space. And the basic theorem of Hodge is that for a compact manifold, the dimension of the space of harmonic forms is the Betti number. So the Betti number can be interpreted or characterized differential geometrically in terms of harmonic forms. By the way, this operator d delta plus delta d, you can also understand it as d plus delta squared. Because d squared is 0, so delta squared is 0, only term that survives is the cross term. This is actually the square with first order operator. And that's very important for index theory elsewhere. The first order operator does not preserve degrees. It only preserves the parity of degrees. It will preserve even forms and odd forms. But when you want to look at the Euler characteristic, that's all you want to do really, because you want to calculate the alternate sum of the dimensions. All the even ones get a plus sign, all the odd ones get a minus sign. So the Euler characteristic is what's called the index, or the operator d plus delta. But you needn't worry with that. It's the definition Hodge gave is this. And there's of course great interest in differential geometry, particularly in case of algebraic varieties and complex manifolds. This theory of harmonic forms ties in all sorts of beautiful things, going back to Riemann, and so on. Now, this gives us a way of understanding what to do for a universal covering. The universal covering of a manifold, a Riemannian manifold, you lift it up. Locally, it looks the same. So you lift up the metric. You have the same metric locally. So you have a Riemannian manifold, which is not compact, but it's not complete, which means that you can't get to the boundary in finite time. And on this, you could look at the same equations, because the equations are defined locally. And you define the Laplace operator and the harmonic form the same way. But now, because the space is not compact, the theorem that the result space is finite dimensional is false. Yeah. This space will be infinite dimensional. They will be Hilbert spaces. Well, subspaces of Hilbert space. And so the dimension is for ordinary dimension is infinite. And so this is the one where you have to get some new theory which will allow you to define a relative dimension, the dimension relative to the fundamental group, which is finite. And actually very simple, and I mean, you can throw away von Neumann algebra at the end of the day, you just take the definitions very concretely. But let's keep the von Neumann algebra because it's useful in general. Now, so in our example, we take the fundamental group, which I call gamma, of the universal covering, or the original space, which is the covering group, and we'll talk about the von Neumann dimension of operators, or sorry, von Neumann dimension of subspaces of the Hilbert space on which the group gamma operates. So they're gamma modules. And now whatever you know about these harmonic forms from their definition, it's clear that they are invariant on the gamma, because the gamma is a group that translates above the base. And if the equation that says it's harmonic is invariant on the translation, because the metric comes from below, so they obviously are invariant on the gamma. And because of that, you can talk about the gamma dimension, the von Neumann dimension. Now, let me make it more concrete. So what is this von Neumann dimension for the case of discrete groups? And, well, I will come to that in a moment, but first of all, once you've defined it, then of course you can talk about the Euler characteristic relative to gamma, the von Neumann Euler characteristic. And so you can define the Euler characteristic. So we'll define the Euler characteristic of universal covering relative to gamma. And the main theorem of the paper that I quoted says that the Euler characteristic of universal covering relative to gamma is equal to the Euler characteristic of the space you started with. It doesn't change. But be careful, this is a non-trivial theorem, it has a non-trivial context. For example, suppose you take X to be the Riemann surface of genus at least 2, then the corollary of this theorem is that because the Riemann surface down below has negative Euler characteristic, that means that the one above, which is defined by harmonic forms, well, there are no zero forms on a non-compact surface, because it would mean a harmonic function. And harmonic function would be constant, and that's not in L2. So these what we're talking about are harmonic forms which are square integral. There are no zero forms, and by duality there are 2 forms. The only possible forms that can exist are in dimension 1 in this case, there's no other dimension. And because the Bethe number is actually, Euler characteristic is actually negative, we deduce that middle dimension harmonic forms do exist. They're not zero. So we have an existence theorem coming out of this, which just says that on the universal covering of a Riemann surface of genus at least 2, you lift the metric, and there are harmonic square integrable forms, non-zero. That's a non-trivial theorem. You can find lots of harmonic forms, but they won't be square integrable in general. So this is a deep theorem in some sense, and you get it as a cheap corollary out of this theorem here. And that actually it's been applied later on. I read a paper of Wilfried Schmidt, where we apply this in the context of semi-simple groups, and he gives you the distance theorem. The distance theorem is really quite hard to prove by direct methods, but this is a topological proof using these von Neumann algebras, which is a bit of analysis hidden inside. So they emphasize that this theorem has a non-trivial content. Now, in fact, if you take on your Riemann surface X not just any old surface metric, but the constant curvature metric, there is always a constant metric of constant scalar curvature. These are the ones whose universal covering is exactly isometric to the hyperbolic plane. And that hyperbolic plane has a transitive group of isometries, which is in fact the group SL2R. And the harmonic forms for that metric are then not only invariant under the discrete group gamma, but they can invariant under the semi-simple real Lie group SL2R. And what they are, in fact, is they are irreducible representations. The particular one we've got here, harmonic forms, is an irreducible representation of that group. And the theory of irreducible representations of non-compact semi-simple groups is a vast industry. first developed by physicists for interest in physics, and then by mathematics, Harish Chandra, Langland and so on, is a very important part of mathematics. And so you see this theorem begins to make contact with interesting things of that kind. I'm not going to emphasize that as a byproduct. But to show you that this theorem of load looks harmless, is in fact quite powerful in terms of its relevance to harmonic spherical forms. Yeah.
On the L2 harmonic one forms in the universal cover of this surface, do you have an action of the group gamma that is non-trivial? So you get an orbit of, if you have one, then you can find more just by acting.
It's L2R actually. These type of gammas always come with L2R.
Okay.
So they have a non-trivial representation of the, and by the way, when you deal with harmonic one forms or holomorphic one forms, there's not much difference. One is twice the other, and the theory for holomorphic forms, you generalize to higher dimensions, would be another example of an elliptic operator. But here we're going to focus on the simplest case. Okay, so that's to show that theorem has non-trivial content. Now let me tell you a bit more about the von Neumann dimensions. We're coming into them sideways. So let's start with elementary algebra and analysis. We'll talk about traces. You know what a trace of a matrix is, some of the diagonal elements. But more intrinsically, if you have a Euclidean n space, think of it as a finite dimensional Hilbert space, and you have a subspace, linear subspace, V, we will have a dimension. The dimension will be anything between 0 and the dimension of the space n. And you could consider the orthogonal projection onto that space. That's called a projection operator. A map of the space H into itself. When you square it, you get the same thing, and that's projection onto the subspace V. And relative to triviality of finite dimensions, that the dimension of that space V is just a trace of the projection operator. So dimensions are special cases of traces. If you have a trace of any matrix that has a well-defined trace, if it's a projection operator, what you're doing is defining the dimension of the space onto which you're projecting. So dimension theory is as a byproduct of trace theory. Now for the usual trace on Hilbert space, if you take a Hilbert space, ordinary Hilbert space, closed subspace, the usual traces, dimensions give you only, if it's finite dimensional, you get 0, 1, 2, up to any integer n, and if it's an infinite dimensional space, you get formally infinity. Those are the traces you normally get in Hilbert space theory. But von Neumann discovered context, general context, of von Neumann algebras, in which you get a theory where the dimensions, to be defined shortly, are real numbers, anything between 0 and infinity. They can be finite and they can be infinite. And an example of such a situation is precisely what we have here. You have an infinite discrete group, gamma. If you have an infinite discrete group, gamma, then you can think of the Hilbert space of little L2 square summable functions on the discrete group. That's Hilbert space. And on that Hilbert space, the left translation by gamma obviously acts. So there's right translation. So you have these two sets of operators which act on the L2 Hilbert space, and because of the associative law in a group, they commute. Left translation and right translation commute. And so, if you look at the left translations, I call it L gamma, and you look at the things that commute with L gamma, then you certainly will find all the R gammas. And the theorem is that what you get is exactly all the operators you get from linear combinations of the R gammas and taking the closure in some topology. And the topology you need is what's called the weak topology. And this is very, very technical. And you see, don't impress me too much, but I think I know what the weak topology is. Basically, it means that if you write it as a matrix, all the matrix coefficients converge. It means that if you take an operator, take it this vector and scale product with a fixed vector, then you get numbers, and those numbers converge. So the commutant, the theorem is that the commutant of all the left translations is the weak closure of the linear combinations of all the right translations, and vice versa. So you get two algebras, we call them AR and AL, which are neutral commutants, and they are both closed in the sense that they contain all the weak closure of any sequence lies in the algebra, and they are self-adjoint in the sense that every operator its adjoint lies in that algebra. And these examples are weakly closed self-adjoint algebras are von Neumann algebras. Von Neumann algebra can be defined that way. But here I've given you them obviously in terms of arising from a discrete group, where it's quite clear what they are. They are things generated by left and right translation, and then taking weak closure. Mind you, taking a weak closure is not a simple thing as it seems. It's quite a lot of hidden analysis in there. You've got to take limits. So it's not algebra. I mean, if you have a group, left translations, right translations, form a group algebra, that's finite combinations, that's algebra. But if you have an infinite group, you can take closures in the Hilbert space sense, and then you get into analysis. And this is then a branch of analysis. You've got to be careful about the continuity. So, now if you apply all this to the subspace of L2 harmonic forms on the universal covering, that's exactly a situation where these are preserved by the projection operator onto the space of harmonic forms is preserved by gamma. Therefore, it will have I should have said on this algebra. On the algebra R and AL, the trace is defined in the following way: for a single right translation by gamma, then the trace is defined to be 0 unless gamma has the identity. It just picks out the identity component. Then by closure you go to the whole thing. So the trace is defined in that obvious way, and then you can prove that the projection onto the space of harmonic forms has a trace, and that trace is finite. And that's then called the dimension, obviously. By the way, if gamma has the infinite discrete groups of many different kinds, but typically many they have not cumulative at all. If you take the SL2, that fundamental group of Riemann surface, it typically has no center or a very small center. So gamma, if it has no center, then these von Neumann algebras are what's called factors. The reason for that is that the general theory of von Neumann algebras tells you can factorize into irreducible bits. Irreducible bits are the factors, and they play the role like prime numbers. So the factors von Neumann classified, he showed there were factors, ordinary factors, which are finite matrices, and they could be either finite or infinite in size. They're called type 1, Roman 1, or Roman type infinity. Also, or they can be type 2, 2, 1, or 2 infinity, in which case the dimension is a real number, or there were some bizarre ones, or appear to be bizarre ones, called type 3, where the situation is more complicated. So this is the theory of von Neumann algebras. It's just outlined very quickly, but as I said, you'll shortly see that you don't really need to use that theory, because everything here is very concrete. So to see how concrete it is, let me remind you a bit about some elementary analysis. And if you have functions on a space, any kind of space, where you have an integration, then you can form operators by using a kernel function. A kernel function is a function k of x and y, defined by 2 points in the space x and y, and that defines an operator, capital K, and that operator is defined so the value of k on a function f at a point x is got by simply taking the value of y multiplied by the kernel function and integrating over y. Average over y, this gives you a function operator. This is the operator defined by the kernel. And the theory, most decent operators have kernels of a. I mean, the kind of properties of that kernel function will determine the properties of the operator. But if you have very nice operators, they'll have very nice kernels. Now, if you've got a manifold x, then if you have a function k of x and y which is smooth, let's say differentiable of high order, then such an operator, such a kernel function defines an operator k which has a well-defined trace. And the trace is got, as you would expect, by putting x equal to y, integrating over x. Integrate the kernel function over the diagonal. For discrete sets, that's the way you summing the diagonal elements. So the trace of an operator of the kernel is the integral of the kernel over the space. So that's for now the smooth kernel. Now the point is that if you have the theory of harmonic forms or the theory of solutions of any elliptic differential equation, this is where ellipticity comes in. The projection onto the solution of the differential equation have a smooth kernel, and therefore you can form the integral of k of xx, and if you're over compact space, that will be finite. That will give you the dimension, genuine dimension. So you relate dimensions to traces of kernels. And the theory of the elliptic equation comes in telling you that the space solution is so well behaved that every solution is smooth and the kernel function is smooth. The integral is defined by integrating the smooth kernel. And that's the theory for a compact space. Now, of course, if you have a space which is not compact, you can do much the same thing again. If you replace x by the universal covering, and the gamma is an infinite fundamental loop, then the projection operator, called K tilde, onto the space of harmonic forms, the solution of the Hodge theory, these are a gamma invariant, and the Hodge theory is harmonic solution, so the projection operator has a trace. Now, has a kernel function which is smooth. And you took the normal trace, you would integrate this kernel function over the whole of the universal covering space. But because the universal covering space is not compact, this kernel function is invariant on a gamma, you're really doing something stupid. You're integrating the same function over an infinite number of periods. So if you take the circle and replace it by the line, you would take a function defined on an interval and simply take infinite many copies. Sensible thing is to define the integral over a fundamental domain. So if you take the circle covered by a line, the fundamental domain is an interval, you integrate over it. Doesn't matter which interval, because every interval translates into every other interval of the same length. So you can define naturally a dimension or trace relative to gamma, because gamma is the thing that translates, by integrating only over the fundamental domain. So the end of the story is that in this situation, the definition of these dimensions over gamma is quite simple. You just go to the universal covering, take the projection operator onto the harmonic solution space, L2 solutions, and that is take the kernel function of that, restrict it to the diagonal, it's now invariant on the gamma, integrate over the fundamental domain, which means that you can just think of it as a function on the Gaussian space and to get a finite integral. That is the definition of this. So forget von Neumann dimension, this is the definition here. But if you want to know where it comes from this general theory, part of general theory of von Neumann algebras. So here we are. Now, you might think it's all rather trivial and obvious. There's a caveat which you should watch out for. So here we say that the kernel function of the projection operator is gamma invariant, it's smooth, this gives you already a function which is invariant on the gamma, so it really a function that comes from the base space. And we're defining the dimension as the integral of that function on the base space. But the caveat is that you be very careful. This is not the same as taking the integral over the base space of the kernel function of projection on the harmonic solution on the base space. The projection on the base space gives you the L2 function down below. The projection on the space above is concerned with the L2 functions above, which is invariant on the gamma. Those are far from being the lifts of the L2 function below, because L2 function has to decay. If you lift anything below, it repeats. Not the same. So the spaces that we're talking about are quite different. So the dimension means the dimension, or Neumann dimension we're defining for HQ is not at all the same as the dimension down below. They're quite different things. One is concerned with dimensions of fundamental spaces, the other is concerned with the Neumann dimension of the infinite dimensional spaces. But, and the theorem, part of the theorem is, their Euler characteristics are the same. The alternating sum of these is the same as the alternating sum of those, but the individual terms are not necessarily. They are the same. So the theory is not very easy to see examples where these Betti numbers are not preserved like that. And the best way to think about that is this. If you got a finite group gamma, to go trivial case, then when you replace space by its finite covering, Euler characteristic just multiplies by the degree of the covering. If you think of it in terms of triangulation of cells and simplicity, it's obvious. So the Euler characteristic multiplies by the degree of the covering. By the way, the intelligent way to do that is to renormalize by dividing by the order of the fundamental group, then saying the Euler characteristic doesn't change. That's the statement that remains true in the infinite case. Now think of the case of a circle. Just circle, take a double covering of the circle by the circle. Now, what is the homology of the circle? Homology of the circle is trivial as one generating dimension 0 by developing one dimension 1, nothing else. While it has is 0, of course. Go to double covering of the circle. It's still a circle. So the Betti numbers are still 0 and 1. They haven't multiplied. They haven't become 2 and 2. They're 1 and 1. Of course, the order characteristic is the difference. So it's trivial 0 in both cases. But it's not the same saying that the Betti numbers are the same. So even this most trivial example, so the Betti numbers below are not the same necessarily in any way as the Betti numbers above. Not a priori, but who knows? God might be, acting devil's advocate. He might sort of be leading you on, and you expect the answer no. But for example, Riemann surfaces. If you the Riemann surface of genus G, you take a finite covering by another Riemann surface, genus G prime, then the Euler characteristics are the same up to a factor of the degree of the covering. So if you renormalize, you get the same answer. But the Betti numbers don't behave that way. The Betti numbers are twice the genus and twice the other genus, and the genus doesn't multiply by n. It's 1 minus the genus that multiplies by n. So you see, this what apparently looks harmless theory of going universal covering has a sting in the tail. The Euler characteristic behaves in a nice way. The individual Betti numbers are quite different things. So this is where the theorem of the paper ends, where the questions begin. So I raise these questions. Question 1, are there examples where the Betti numbers are in fact not integers? In other words, where the von Neumann theory of real numbers really happens. Maybe the Betti numbers are defined as real numbers turn out always to be integers, or perhaps not integers, maybe rational numbers. Who knows? In simple cases, for example, in the case of the Riemann surfaces, you see that the universal covering of Riemann surface of higher genus is it has neither harmonic 0 form nor harmonic 2 form, only has 1 forms. The 1 forms therefore give you the Euler characteristic, therefore their dimension is integers. So for even the surface case, the dimension is an integer. Although it wasn't defined as an integer, it has to be an integer by topological reasons. But it has only dimension 2. What happens if you go to dimension 3 or 4? Will it be true still? That was the question I didn't know the answer to. Well, and so I raised this question, and not only for surface but in general. We know that the Euler characteristic is an integer. Well, how about the individual Betti numbers? Are the Betti numbers, in other words, the square integrable harmonic forms, do they have von Neumann dimensions? Are they real? Are they integers, rational numbers, or can they be general real numbers? And it wasn't trivial to get examples, because the most trivial examples, you see, you get it, even though you shouldn't necessarily get it. But philosophically, this theory of von Neumann is known to exist in general. The real numbers they're around. In my heart of hearts, I certainly hoped there would be real numbers. The theory would be interesting. If it was always integers, you feel, well, this is somehow not quite as exciting as you think. So I left this as an open question. Now, what I was very annoyed about was later on, people called this Atiyah's conjecture. And what they made of the conjecture was that the numbers should always be integers. Now, that wasn't what I believed. I believed the opposite was true. And then people came along and said, disprove the Atiyah again. I liked that a bit much. And they had the strong Atiyah again. And I was hoping for the opposite. They gave me the wrong conjecture, and then they disproved it. So I'm not claiming I made a conjecture, I raised a question. And the question has interesting answers, but I think people learn now that you shouldn't call it a conjecture. It was a question. Question can be, you could maybe hint that you believe the answer is this or that, but I didn't say anything about what I expected. I just raised the question, do they exist? So, and of course, by the way, when you go beyond dimension 2 to 3, 4, you don't need to go very far, because topologists know that every finitely presented group can appear as a fundamental group of a 4-dimensional manifold. So you don't need to go above dimensional. For 3 manifolds, there are constraints. Fundamental group of 3 manifolds are not generic. But the fundamental group of 4 manifold can be anything it likes if it's finitely presented. That will be, I think Grabowski will say more about that. So you don't need to think that this is a problem about 10-dimensional manifolds or 12-dimensional manifolds. Stick to 4. is quite small, really. Physicists now like to be in 11 dimensions, but they can go back to the old-fashioned and go back to space-time, and they're in 4 dimensions. So, that was the first big question, and at that time, I hoped the answer would be interesting examples, but nobody knew. Second question was this. Well, let me say, go back a second first. The question originally was not only about the Bethe numbers, which is Hodge's theory, but any solution of any elliptic equation. And there are many other elliptic equations, for example, holomorphic functions, holomorphic one-forms on complex manifolds, and the theorems there, index theorems are the same. You can ask the same questions, there's Neumann dimensions. So you can ask this question about all the families of elliptic operators which arise in differential geometry. But the particular one which comes from Hodge's theory is related to homology, and so you have another handle on that. Well, the other handle I have on that is ordinary homology can be defined by simplicial methods. You count the number of simplices and so on. So this is the most concrete, simplest example of the question. And this is the example which people are focused on. And those are called the Bethe numbers, relative to gamma. Now, for a compact manifold X, we can define homology analytically by Hodge's theory, but you can also define it in counting simplices by triangulation, and it's the same thing. Homology. First theorems Hodge proved, before that Durand proved that the differential forms give you the same homology as ordinary simplicial theory over the real numbers. But is the same true for non-compact manifolds? In general non-compact manifolds, the answer is simply no. Square integral forms will depend on the metric in a special way. For the universal covering, the metrics that come by lifting are a very special class, invariant on the fundamental group. So you might hope that the theorem that the harmonic forms, harmonic Bethe numbers, give you the same as the simplicial homology, again relative to gamma always. Gamma acts both if it acts smoothly, but on acts on harmonic forms. If it acts simplicity, it acts on the combinatorial ones. So the question is, are the Bethe numbers the same, both simplicity and analytically? And I raised that question. That one was answered very quickly. In fact, in the paper when it appeared, I was able to say that it would be proved by Dodchuk, who studied in general combinatorial and differentiable homology, and the answer is correct. The combinatorial L2 theory is the same as the Hodge's L2 theory. That enables you, if you like, to get away quite quickly from analysis of differential forms, deal only with the kind of analysis you get in little L2 of gamma and the weak limits on acting on the group algebra. And I think obviously we'll say that first of all. If you want just to deal with the Bethe numbers, not other differential equations, other operators, you require other differential operators which you can't express combinatorially. If you're only interested in the homology, forget the general differential theory, focus on the combinatorial theory, and for the combinatorial theory you can formulate precise questions to do with infinite discrete groups that have nothing to do with manifolds. But the interesting application is for manifolds. But you can focus on the combinatorial session. Now the third question, which I raised at the time, is we know that ordinary homology groups, the Bethe numbers of manifolds, are not only topological invariants, but they're even invariants of homotopy type. Two manifolds of the same homotopy type can even be diffeomorphic or even homeomorphic in general, and we know that the Bethe numbers are the same. They're unchanged under homotopy. And so you can ask, is it true, the same thing true for these gamma Bethe numbers? Are they homotopy invariants of the underlying original space? You start with space X, compact, has perfectly good Bethe numbers, go to the universal covering, it has these gamma Bethe numbers. If you replace X by Y, where X and Y are homotopy equivalent, if they're homotopy equivalent, they have the same fundamental group, replace the universal covering of X by that of Y, do the same things on both sides, you get the same answer. Well, interesting question. I think I expected the answer to be yes. Certainly after Dodchuk's result. But essentially these are all problems to do with the little L2 of gamma. That's what this. So at this stage you can throw away analysis in terms of differential equations. You still need analysis concerned with operators and weak closures, Hilbert space theory, and you're dealing with infinite discrete groups. So this then becomes now the theory of infinite discrete groups and their group algebra, not as an algebraic object, but as an analytical object inside Hilbert space. But I think the examples of manifolds give you the sort of meat and gritty, the background, much generalization. So, if it wasn't for the manifolds, we wouldn't have got to this. Somebody could have asked this question long before, but without the example of the manifolds, you wouldn't have had the same kind of punch. So that's how the questions arise. These are the questions that I formulated in that paper, in which I think a lot of progress has been made, in which Grabowski will explain how much has improved, how much has not been improved, and how much interest there is in it. And when I heard about the latest results, I was very struck by the fact that when you get to the answer to these questions, you come up against questions concerned with logic and computer science. You end up with things like Turing machines. And actually this conference I went to was a conference full half mathematicians and half computer scientists. And the people there were sort of doing both. Of course, it being Turing's centenary, Turing was very much in the air. So having things related, I'd never come across anything in my work related to computer science or Turing machines. I knew about them as a general culture, but I never expected to meet them in the flesh, so to speak. So here you will see that they appear in the flesh. We actually have to talk about things like Turing machines and systems to answer these questions in a correct form. So I was very excited by this development. I thought you should hear about it from experts. And so in between, in that 40-year period between then and now, a vast amount has been written on all aspects of these questions. And my conjecture has been raised to, my question has been raised to the level of conjectures, and strong conjectures and weak conjectures, and big theory conjectures. And so I was obviously followed this with interest from a distance. When I heard about these results, I seem to be quite sufficiently definitive. We're not quite close to the book, but it's answered. So I'm luckier than Fermat. I lived to see my conjectures, or the conjectures I did. I think Fermat did make a conjecture. He said more than he proved it. He was the strongest kind of conjecture. You could say, I think I proved the following theorem. I didn't say anything like that. But anyway, it lasted quite a long time, and if you ask a question that generates interest for the next 30, 40 years, get lots of people their PhD theses. A lot of people have got their PhD theses on this question. Lucas, I think, is one, and probably that's yes. So, it's not useful for anything else. It's useful to get
Any questions?
Oh yes, as I said, the difficult questions will be, I'll pass them on to Lucas. You know the famous story about Einstein and his driver, I suppose?
No.
Einstein used to go around and he was famous giving talks about relativity theory. And he had a chauffeur who would drive him round. And the chauffeur would sit in the audience and listen to all these lectures. After a while, Einstein said to him, John, you've listened to so many of these lectures. If we go to some place where I'm not known, you could give the lecture yourself. And I'll sit in the audience. So the guy said, fine. So the next time they went, the guy gave the lecture, and questions were answered, and he knew how to give the answers. So one time he gave a lecture, somebody asked a question that he didn't know the answer to. He said, that's such a stupid elementary question. I'll ask my chauffeur to answer the question. No, I'll ask my chauffeur to answer the question. But no, if there are any really easy questions, I'll deal with them.
Are there any questions?
Yeah.
Jose.
So, in the 90s there were these Sen conjectures about existence of alpha harmonic forms on monopole moduli space.
Yes.
Of course, the non-compactness there is different than the non-compactness
Yes,
here.
of course.
So, I don't know what this status actually of this is. I think there are a lot of explicit calculations which show in the Atiyah Hitchin manifold, for example, that they do exist.
Yeah,
But in general, what is the story?
Yeah, the manifolds can be non-compact for many reasons. I said there are one class is those which are infinite coverings of compact manifolds. But that's a special class, that's periodic. But there are other classes of manifolds which are non-compact in a very different way, which are not, where there's no discrete group and the manifold is simply has a metric which is complete, but it goes to infinity, and it can have very complicated behavior in infinity. And those manifolds occur in lots of interesting cases, because compact manifolds are, we have to be honest. We study compact manifolds mainly because we know how to deal with them. And most manifolds in the world which occur, for example, the manifolds which occur in these problems in physics, occurs what they call moduli spaces. Moduli spaces are the parameterized spaces of solutions of equations, like elliptic nonlinear differential equations. You look at solutions, the solutions depend on some of the parameters, very often finite. If the equation is linear, you get a linear space, you have a dimension. If the space is nonlinear, you get a non-complicated manifold, and then typically those are non-compact. And so non-compact manifolds do occur very naturally in life, or physics, whatever you like. And questions about whether the square integral forms exist on these manifolds, and what their relationship with homology is of very broad interest. Now, these manifolds, as Jose was referring to, have been much studied and a lot has been proved about them. There are some results in some directions. I mean, I've forgotten which way around it is, which one implies the other, but not the full theorem. So it's not true in general that Hodge theory applies to complete non-compact Riemannian manifold. Some part of it applies, other parts don't, and you have to work hard, and in lots of special cases you have to do it by some other methods. These methods, this theory doesn't help there because these are different class of manifolds. So when I said non-compactness is not a property, the absence of a property, there are many, many classes of manifolds which are interesting. Well, questions about L2 forms are of interest, and some of them solved are not. For example, the kind of examples that like generalize the upper half plane or the hyperbolic plane are the symmetric spaces, the groups, a real semi-simple group divided by a maximal compact subgroup. And these are uncompact, and very people would be interested to know the manifolds are on. But because those have like a high degree of symmetry, these methods here apply. There are discrete groups which have compact quotients.
In the same conjecture, you also have an action of the modular group. So that's why it seems similar to this setup that you were describing. It's not acting as cover, fundamental group of anything, but you do have an action of this discrete group, the modular group of elliptic surfaces, acting on L2 of the.
Yes, you're right. You're right.
You have to put all the moduli spaces together. Now, taking all the charges, but.
Yeah, I mean, there is a connection between representation of discrete groups and these things. In general, you have a manifold which is the discrete group acts, and it says invariant metric, then the harmonic forms will be acted on by gamma, whether or not the quotient is compact or not. In fact, very often, so that you get interesting examples of representations on Hilbert space of infinite discrete groups, and some of them are definitely not rising from compact manifolds. No, there's a very big theory there.
If I'm mistaken, I'm trying to remember, didn't Tim Austin recently produce an examples of where there are L2 Beatty numbers that are transcendental? This is what
well, that's what he was
exactly what's going to happen.
Yes, exactly.
Exactly.
That's right. So I mean, when I asked the question,
I have a lecture next hour. That's why I want to do.
Oh, I see.
yeah, well, I mean, I tell you, I mean, I was interested, of course, whether these Beatty numbers are real,
Yes.
real numbers, and I had no idea whether they went beyond rational numbers. So I hope they would go beyond this, and then you ask which kind of real numbers can you get?
Yeah.
Algebraic numbers, transcendental numbers, but the theory is, of course, that you can get any number that can be used by a Turing machine.
Right. Okay.
So they really are pretty general numbers, like computable numbers, and they're much beyond intuits. There are lots and lots of interesting examples. But you hear that you have to pay your ticket for the second part.
Good introduction to the second talk. It should be exactly half an hour, unless there's no more questions. I should say that I don't know whether you'll be perfectly pleased that your conjecture has now been called the Atiyah problem.
Yes. Oh, no, absolutely.
That's all right, isn't it?
Of course, I raised the question, it was a problem. And I didn't want to prejudge the answer by making any stupid conjecture. So it's good moral. You can let people associate it connect to your name, but don't do it yourself. You might know, then you can change your mind about it. Somehow he made a bit of a move, he said he proved it.
Very good. So thank you very much.
Okay.